This is AE 597 with Professor Krishnamachari on Wednesday, July 13, 2016.
Okay. So I wanted to talk a little bit about the midterm exam. And I haven't graded all of the exams yet, but from the ones that I have graded, I think questions 2 and 3 in particular seem to have been challenging. And I think what's common to both 2 and 3 really, I mean, besides question 1, which is just the concepts, and question 4, which is sort of a very clean, recipe to follow, both 2 and 3 required several elements in common. One was kind of doing some modeling of the problem. Sort of identifying relevant, in one case it was sort of expressions or conditions. And in the other case, it was really formulating the optimization problem. And also, I think the other skill that these questions were really getting at is that both of them had at least like part B of question 2 and really what question 3 added to the standard water filling is stochastic channels. Right. So I was going to go over these two problems, at least maybe not work out all the details of it, but sort of at enough level of detail that it's clear how they would be solved. But it's not really about questions 2 and 3 on the exam. It's really about what's the takeaway for the future. Like once you're done with this class and you forgot everything in this particular exam, what would be a useful nugget in there that's still valuable and that has value beyond, again, just this particular exam, right? So one comment I want to make with respect to the problems involving stochastic modeling is, of course, goes without saying, is that it really needs the 503 prereq, right? This is, in fact, probably in the networking curriculum today, with the exception maybe of E550, really the only class in the master's program where you actually apply what you learn in 503. If you're taking the bulk of your courses, particularly in communications, in networks at least, I don't think virtually any other course really requires you to go back to 503 and use the concept. So we're using 503 ideas here.
Excuse me, Professor, sorry to interrupt, but can you put the mic a little higher in your shirt, please?
Sure.
Thank you.
So the question is sort of what should you have retained from 503 now that would help here, and then also then think about beyond this class, if you're out, of course there's no way to predict what environment in terms of industry or academia you might end up with afterwards, but what long-term is meaningful with respect to stochastic modeling to take away from your master's degree even. So I want to kind of get at those two issues a little bit. Because there's a lot of perception, certainly, that increasingly all the jobs out there are software jobs. Why do I need to take probability? Why am I working out expectations of things? What has this got to do with anything in the real world? So I want to address that concern a little bit. So specifically in wireless networks, why do we care about? Why do we bring in probability into wireless networks, right? So I think this is okay. And how much do we really need? Okay, so in both of these two problems, where the probabilities showed up was in one case we said there is log normal fading, and that was really, if you think about what log normal fading is fundamentally about, is it saying that the channel quality is random. And question 2, which is about like the placement of base stations or the reuse distance that you need so that you can have both cells operate without interference. Part A solves that problem without worrying about the randomness of the channels. Part A says, let's forget about the fact that things are random. I just look at on average, how do the channels behave, and I'll answer that question. Okay. But Part B says, but we know from our experience, and we know from measuring data on real cellular base stations, that there's a lot of variation in the signal strength. Okay, and I can measure that, and I can actually evaluate what the variance is. I can fit it to distributions, and if I do it in the dB scale, it looks kind of Gaussian. Right? So I actually know that in practice, not only do I get a certain average value, I'm really getting instances that are distributed around that average value as this particular distribution, right? So the real world has this randomness of channel quality. It's not something we're cooking up to make our lives miserable in this class, right? The channels are fundamentally stochastic. They have those distributions. And the design problem we're addressing is a real design problem because it's really asking what's the reuse distance. So for example, in the conflict graph that we were creating, we're saying these two cells, like if we take an example and we say, here's my set of base stations, and in class we said, okay, if they're right next to each other, we're going to say that they conflict, and so we created like a graph based on the map, looking something like this. But that was actually a toy example. In real life, what you have to do is to say, are these two base stations actually going to interfere with each other, or are they not? Right? And it's not actually a question of are they neighboring cells or not. It's a question of how far apart are they. So of course, if they are neighboring cells, clearly that's a problem because you can imagine, some node at like halfway between those two base stations, and it would get as much signal as it would get interference. That's probably not tolerable. So certainly, maybe these are going to conflict, but maybe there's a question of, is this base station going to interfere with this base station over here or not? Right? We can't take for granted that they won't, because maybe the cell in here is really small. Right? Maybe the amount of interference actually is going to be quite large. So even for this real world problem, we've taken kind of a simple approach when we did the graph coloring, saying, we know the conflict graph. But in the reality of it, how do you figure out the conflict graph for where base stations are placed, is you're going to have to deal with the fact that the channel variation is noisy, and you have to figure out, are these two sufficiently far apart that if I give them the same channel, all of my users will be happy. Despite the fact that sometimes the signals are very strong. Which means, in particular, in this problem, like in problem 2, the concern that we're really trying to deal with is if you look at the two base stations in question, and we said, assume this was a simplifying assumption so that we can do some calculation with it, that they both, and I made this a little bit bigger, but they both have the same radio range. And you kind of focus on the worst case interference would be for some user at the edge of the cell, right? Because its signal strength, the mean value itself is as small as possible. And then on top of that, it might be closer to the other base station, right? So this node over here would be sort of what's called the edge user, cell edge user, experiencing the lowest SINR. Okay. So what can happen? So if the channel quality is not just the mean value but also varying, the worst SINR it might experience is that the signal quality from the base station is not good. You're experiencing a fade, which means that from that distribution, like instead of getting the mean value, you're getting significantly below the mean value for the signal. And likewise, from the interfering base station, for worst case scenario, it's like given this statistical variation in the signal, you might experience at some moment a very high value of interference. So on the one hand, just from the distance alone, you might be getting a certain SINR mean value. But on top of that, the signal might be below its mean value, the interference might be above its mean value, right? And you can imagine, like, under different circumstances, the signal will have different values, the interference will have different values. So the SINR is going to have different values. The SINR itself is going to be a random quantity, right? And so we're asking this outage probability question is, what's the probability that this SINR is so bad that I can't even communicate? And if these two base stations intuitively were too close, we won't be able to communicate, right? But adding in this variation in the channel quality is actually complicating our life. Because now we're increasing the chance, on the one hand, that the signal might be dropping, and we're increasing the chance that the interference might be high, right? At the same time, at other times, it might be the opposite, meaning the signal might be strong, the interference might be low. But from the probability of outage perspective, the number of times in which I drop below the threshold when I'm unable to talk on the phone, that's the thing that's of interest to me. And compared to the deterministic model, here it's a probabilistic question. It won't happen all the time, it happens some of the time, right? And in the real world, for wireless users, the world is stochastic. A lot of our problems don't happen all the time, they happen some of the time. And the question is, does it happen sufficiently rarely that I don't have to worry about it? And I want to design my system so that the bad events don't happen all the time. I want to design my system not only to ensure that the bad events don't happen on average, but typically with some like low threshold, right? And so in this case, probably I would want, I said less than some probability P, maybe you want like 1% chance that the SINR drops below acceptable values. Because if you're serving users, you're trying to collect revenue from them, you're running a business, and more than 1% of the time they're unable to communicate whenever they happen to be driving around near the cell edge, that's a bad design, right? And you wouldn't operate very long as a service provider if you had really lousy quality at the edge of your cells. Although having said that, I'm unable to call out of my home. I think I might be at the cell edge and I might be suffering from this problem, and I'm unable to talk on my phone in my home. So, but that may be because somebody there didn't work out their calculations, right? There's maybe some variance that wasn't taken into account at different locations. So it's possible. So from a modeling perspective, from a design perspective, in wireless networks, we can't get away without thinking about the randomness inherent in the problem, right? So it's not just something we're doing to make our lives miserable. It's really fundamental in the design. The third problem, which was about water filling, was also getting at this issue, which is that when we talked about water filling in this class, when we first presented it, we took a very simple deterministic view. And that deterministic view, for water filling, just said that, we have a bunch of channels, here's their, different noise to gain ratios. And we can basically figure out what power level to fill by choosing that water level to be in such a way that uses up all the power, and you're delivering power to each channel. That's the gap between the water level and the noise to gain ratio for that channel. This is good for the standard water filling is only suitable for slow fading channels. What I mean by that is a channel in which the values are not changing dramatically, right? And so what this problem got at was, what if they were changing fast? So if they're not changing fast, what you can do is you can send some signals, you can measure the quality of the signal, then you can figure out these ratios, you can solve that optimization problem, and then run it. But sometimes you may be in an environment where, because of the motion or people moving around or the traffic or whatever, the signal quality doesn't stay, this noise to gain ratio is not always the same value. Okay, in particular, even your noise power might be same, but your gain might fluctuate dramatically from moment to moment as different reflections cancel or constructively interfere, right? And so in those types of settings where you have fast fading, the gain to noise ratios will be stochastic or stochastically varying. And for this problem, we're just taking the simplest possible fading model for, and this is just the channel quality really, right, at the end of the day. So it's really just a fading model we're talking about. And we took a very simple fading model, which is IID over time. And in fact, for the main problem, it's even further simplified to a toy case where there's only 2 channels, and one of them has a fixed value, and the other one maybe has either a low noise case, which is a good case, or it has a high noise case, which is a bad case, and you're sort of 50% of the time in either of these 2 settings. But a point here that I don't know for sure, because I didn't grade all the papers yet, but I was browsing them. But I felt like for some students it was a little confusing as to whether this 50% probability, when it happens, do you know afterwards what situation you're in, or do you not, right? Generally, the only reason to focus on the stochastically varying case is when you don't know, when there's uncertainty. If there's certainty about which scenario you're in, you're just solving that water filling problem each time, the same one we did before, right? There's nothing different about that. In that case, there isn't a single power you would choose. You would choose depending on the setting you were in, right? So sometimes when we do this probabilistic modeling, we ask ourselves, even though it may be varying stochastically, do I know it or do I not, right? If I know it, then even though there is variation, it's not uncertain to me. Then I don't need a probabilistic framework. I just have to solve a deterministic optimization with the correct parameters, right? Here's a different example of where this shows up. So take every networking problem you know of where there's an optimization. So let's take a random one. Let's take, we're going to encounter it, but routing. Okay, so what is routing? Routing is you have a network. There are link costs on the links in the network, and you want to compute the shortest path between point A to point B. If you use Dijkstra's algorithm or Bellman-Ford algorithm, it'll tell you the shortest path between A to B. In order to run those algorithms, somebody has to give them what the graph looks like. Okay, so that's a deterministic optimization. That graph and what the link costs are might actually be varying over time. So there may be certain times when some links are really bad, some links are good. But for Bellman-Ford and for Dijkstra's algorithms to basically give you the answer, those are known quantities you figured out. They're not solving a probabilistic problem. They've figured out the numbers for now, solved it. And when the numbers change, they're going to resolve it. So you might change your routing tree when the link conditions change, right? You keep running them in the background, collecting data, and you keep running. So there are problems in which the channel quality is varying, maybe time varying, but it's not fundamentally being modeled as a probabilistic problem. It's because we don't have uncertainty. We've seen the values, we know what they are, right? But if the changes happen so fast that you don't have time to take the measurement, figure out what the values are, and then solve for the optimum, then they change again, you take the measurement, you figure out what the values are, solve the problem. Then they change again, you figure out the measurement, solve the problem deterministically over and over again. So in other words, there are 2 ways in which we deal with dynamics, right? If the dynamics are slow enough, we can afford to do this, because the cost of collecting the observation, running that optimization might not be very high. But if you're in an environment where that world is changing very fast, by the time you figure out what the gain to noise ratio is in this problem, or the link qualities are in a very fast changing network, the network might have changed. So you're solving the wrong problem then, right? So the time scale at which these changes happen determine whether in practice we're solving a deterministic problem over and over again and solving it, or if we want to use a probabilistic methodology. Right? So the time constant of change determines whether we can solve the problem as a, what I call a, let's say, classical or deterministic or as a stochastic probabilistic. And particularly when we get to wireless networks, the environment changes will be a function of what environment you're in. Some environments actually, this link quality does change very slowly, as we talked about. In other environments, it does change very fast. So if I apply stochastic water filling by estimating the gain to noise ratios in a slow fading environment, that's fine. But if I have a fast fading environment, doing this means that whatever gain to noise ratios I'm using are probably incorrect for the instance, or by the time I learn them, by the time I apply them, things might have changed. Right? So this time constant is really fundamental to whether we need to worry about 503 or not. Right? And in wireless networks, as we're going to higher and higher, I would say, dynamic environments. So if I'm going to put my radios in cars that are talking to other cars, talking to things on the roadside, just as an example, the velocity is now very high. So a car that's driving at 20, 30 miles per hour, talking to some base station, that link quality is changing on the order of, microseconds. And so that's typically faster than even a packet could be sent. So when you're sending that packet, what that gain to noise ratio is going to look like, you have no idea. Right? So you can't deterministically figure that out and then solve the water filling and then do that, over time. You have to solve for uncertainty. You have to solve for the fact that I don't know the gain to that moving node. Okay. But maybe over calculations, over a period of time, I've characterized what the distribution of the gain looks like. And if I can at least characterize what the distribution looks like, I can solve it to improve my expected performance. Okay. So the goal of a probabilistic or stochastic optimization problem typically, right, is you're given some variable that has a distribution. And the performance objective depends on it. Okay. So when we say it has a distribution, i.e. it is unknown or has uncertainty, so the goal is typically maximize the expected performance. Let me give you a simpler example that has nothing to do with wireless networks. So say you're running a store and you just sell this one very specific type of item. Okay. The classic example is lemonades. So you're selling lemonades. People will show up and they'll buy your lemonades, and so you decide at the beginning of the day how many lemons you should buy, how much sugar you should buy, how much basically stock you should have to provide your customers with the service they want. Right? One of two things can happen. It may happen that you have plenty of lemons and sugar stocked up to serve all the customers you got. And it may also happen that you had too much. It may happen that you thought there was going to be a lot of demand and people didn't show up. Or it could happen in the other direction. You might think there's not a lot of people going to show up, and you have a small amount of stock available. It gets sold out. In the first 3 hours you opened your shop, and the rest of the day you have to sit there doing nothing because you didn't order the rest of the stock. You have to shut it down. People are unhappy. Right? So either of those two extremes are bad. So ideally you'd like to operate it at some value that's doing well. So this is an example where you're trying to optimize your system. The system here is running buying the stock for what you're selling, You're trying to choose that number, but you have to optimize it in the face of uncertainty. Because how much you sell, how much you waste, how unsatisfied your customers are, all of these are a function of a variable that you can't say precisely when you're stocking, right? So here, the random variable is that customer's arrival, right? How many customers show up? So we may not know that exactly, but a good store owner over a period of time probably develops almost intuitively a sense for a distribution of that. Maybe even determines other factors that affect that distribution. Right? So they might know if it's a rainy day or if it's a hot day, how that might affect the demand. They may be able to look at weather forecasts and take those factors into account, and they shape their sense of what the distribution is going to look like. They don't assume that exactly 10 people will show up. They're assuming that a range from 15 to 25 might show up. And depending on how expensive the stock is, you might decide just to overstock for the higher end of it. Or, in some cases, the thing that you're stocking is so expensive or you don't even have a choice, you might end up having to stock it in such a way that you just want to maximize your expected revenue and you want to take into account possible customer dissatisfaction as well. Right? Airlines have this problem all the time. They have to decide how many tickets to sell. If they sold exactly the number of tickets as seats as you think they should, the majority of the time they will go with empty seats because people cancel their flights at the last minute all the time. They will book the ticket, they will even check in and not show up because something happened, they ran into traffic or whatever. So it's actually not to their advantage to book exactly the right number of people per the seats. They always overbook, okay? Which is why in times of high demand or with high variation demand, when they are taking all of these into account, you will occasionally find that they do encounter a situation where more people show up than they have seats. And that's when they offer people various discounts and vouchers to sort of try and defer their flight. The reason they're doing that is they're trying to deal with the cost of having overbooked. So in those cases, they have to deal with that issue. But they're dealing with the same problem. They have an uncertain arrival process which has a distribution, okay? And believe me, their algorithms are doing probability at the back of it. Okay, they are maximizing the expected revenue. You'd be stupid to be running $1 million business, billions of dollars in business, without doing stochastic optimization behind it. Okay, so all of these problems where there's something you need to optimize for, but that objective depends on things you can't control, you don't know for sure, you can't predict, but you want to maximize some expected metric. All of those problems involve this type of optimization that we've encountered here. Okay. And in wireless networks as well, we use these types of optimizations. We often design our systems to give us the best expected performance, or in other cases, the best sort of, or make sure the worst case performance is not too bad. So both of these are reasonable objectives one could look for. So in this particular problem, so let me go over both questions 2 and 3 then. So let's look at question 2 first. So question 2 was about these base stations and the cell users. Okay. So we have these base stations, and really the worst case SINR that you care about is for this edge user. And what you're really worried about is that SINR would drop below the given threshold. So what is SINR? So SINR is simply the signal power divided by the interference power plus the noise. And when I'm going to talk about, well, let's talk about both. So if you're doing part A, really it's just a straightforward expression that you need to write. The power level is fixed. I think we specified that in the problem. So the power level is fixed at some P. In the simple path loss, the signal received power is simply going to be that power level times, what was it, R over, did we specify a D0? No, so you can just do that, to the power minus eta, and times some coefficient k, which is your reference distance, and that's the signal component of it, and the interference component of it is also transmitted with some power p, And the interference amount now starts to depend on this distance. So if you say the distance between the two base stations is x, the distance to this other base station is simply x minus r. So that's this part. So this is just a question of having some notation to describe your distances. Okay, plus the noise power. And we want to make sure this SINR is above the given threshold t. And so we're basically asking for what value of x can you guarantee that this would be true. First of all, without even working anything out, it's very easy to see that x has a role to play. So if x is large, right, so the higher x is, the bigger this term is going to end up becoming. And the higher x is, the smaller the interference power is, because it's a minus eta here. So the smaller the interference power will be, and so the higher the whole term will be, which will make it more likely that it will cross the t. So clearly it's monotonically, the SINR being greater than t monotonically should, this whole term over here would monotonically increase with x, right? So that's something that you can see easily. To work out this at this point is just an algebraic exercise. You multiply t by everything here. Maybe you can simplify out the d0 over eta cancels from, no, it won't because there's an n here. Anyway, you just write it all out. You'll just be left with something that's got an, x minus r to the minus eta power, and you can at least express it in terms of trying to solve for that. If you want to simplify it a little bit further, probably the easiest thing to do is try to ignore the noise term. If the signal terms and the interference are sufficiently large, it would be that. But if you kind of, just wrote down this expression and showed some attempts at, isolating some function of x on one side, you will get all of the credit for the problem. Okay. So this was for part A. For part B, the key difference is that it's not just this, but it's sort of, we're adding to it this let's call it, they're both different random variables, one for the signal, one for the interference, and these are sort of your log normal random variables. And for this, I certainly did suggest to neglect the noise power and just focus on signal to interference plus noise. And the insight was the following, that if you look at a log normal random variable in the log scale, it is a Gaussian, right? And if particularly you can ignore the noise term, this ratio of signal to interference, and if I look at this in the log scale, is basically a difference. Okay, it's a dB difference between dBm from the signal power, the dBm for the interference power. What is that difference, right? And we're saying we want that difference to be more than some number. Okay, so this whole thing and this whole thing, these are both, let's call this x1 and x2. They're both, or maybe I should call them something else. Let's call it y1 and y2 are both log normal variables. Because not only is the fading a log normal variable, the total received power is also log normal. It's just shifted by this amount in the dB scale. And so if you were to write, rewrite all this in the log scale, so this was basically the transmitted power in dBm, minus eta times 10 log 10 of r over d0 plus phi1 dB. Okay, so now this is a normal distribution with some variance. It just says with a known constant variance, so just call that sigma square. And minus, this is the denominator term, has a p dBm. Okay, minus eta 10 log 10 of x minus r over D0. In fact, this over D0 just gives you an additional term, and that's the same for both of these, and that'll also cancel out. So 2 dB. And so, a bunch of these terms basically end up canceling out. So this D0 and this D0, because of all of the other terms, will cancel out. So you're basically left with something like this. And so this is the SINR, if you will, in the dB scale, or SIR. Okay. And you can also take the threshold in the log scale, and so 10 log 10 of this T is also just some threshold, it's just TdB. And so the condition we're interested in looks something like phi 1 dB minus phi 2 dB minus eta 10 log 10 of R plus eta 10 log 10 of R minus X should be bigger than TdB. Okay. So what are these two quantities? They're basically constants that depend, and this constant in particular depends on X. This is just a constant if you know what R is. This is a constant that's given to you. So the only thing in this expression that's a random quantity are these two. Right? And both of these now in the dB scale are normal random variables. And from 503, I was hoping you would recall that the difference of two random variables that are Gaussian is also Gaussian. In fact, any linear combination of Gaussian random variables is a Gaussian. Okay. And so if you want to call these two things, let's call it some new value. Y itself is a normal random variable. Okay. Its mean is the difference between the means of these two Gaussians, which is just 0. Its variance will be the sum of their variances. It'll actually have a variance of 2 sigma square. Okay, the variances don't subtract. It doesn't become a 0 variance term. It has actually twice the, the variance is that, right? So you have a Gaussian random variable, and you want to ask, and it has this behavior, and you want to ask, is it bigger than what is going to be on the right-hand side? So we can rewrite this as y is bigger than TdB minus eta. So you're asking, what's the probability that this Gaussian random variable takes on a value that's bigger than this? Well, that's simply 1 minus the CDF for y evaluated at this number. Okay, and so when you compute all of this quantity, that's the probability of. This is actually not outage. So if you want outage, it's just the CDF, right? So probability of outage. You want to look at this condition, in fact, right, for outage. And so the probability that it's smaller than this is the CDF. That's exactly what the definition of the CDF is. So you have a CDF of a Gaussian that you know it has 0 mean and has this variation, and you're asking what's the probability it falls below this value. And everything here you can compute if you know for any given, so if you know R for sure, you know T, X you don't know, we want to find out. But this gives us an equation, right? That's a function of this X. So for every value of X, I can compute the CDF. And what we'll find is as we increase X, the probability that this of outage, let's just say, is as you increase X, it's going to keep dropping. For every value of X, we can compute this. And the way you would finally find it, even numerically, is just compute the X such that this condition holds, that the PDF falls, that the CDF is actually equal to the P. That's your outage probability threshold. So this is sort of the technical detail of how you go about it. But really, if you got to the point of thinking about it as we can rewrite it in the log scale, we can write the two terms, and what you're left with is something that can be described by Gaussian, then you would have gotten most of the, if not all of the points. You know, I think depending on how far you got along this line of thinking, that's at least what I was looking for. So in this case, writing a very clean closed form expression isn't possible, not least because it's a Gaussian. We don't even have a closed form expression for the CDF. Right? The other question I asked is what would happen, you know, to the distance between the base stations as the variance increases. And it's actually not an obvious, there's no obvious answer actually for it, but there's an intuition, and I would give credit for the intuition, that as you increase the variance, this interference can sometimes take on very high values that you would intuitively expect, at least in those conditions, for the net SINR to be even higher than you would see, lower than you would see in the deterministic case. But at any rate, at a minimum, it's obvious that as you increase X, you're, you know, reducing that probability below a threshold. Depending on what you chose your threshold to be, this distance might be more or less than the average case. So certainly if I chose a very small threshold, you would imagine that I would need a farther separation between the base stations. But if I chose a very high threshold, then I don't need them to be apart by much because I'm okay to tolerate, let's say, very high chance of outage. So it would actually depend on P. So the answer to that question was sort of it depends on P. But if you had the intuition that at high variances for small values of P, you're going to need a bigger distance, that's really what I was looking for anyway. So that was for the problem involving the base station location. For question 3, from the exams that I browsed, I haven't graded them again, but I did browse a few. A common source of confusion I found was where to put the probability in the optimization. I think a lot of people did get the idea that it's now become a probabilistic optimization problem, that when you write how to maximize the expected sum, that really there's sort of 3 types of terms to worry about. There are terms that look at like log of 1 plus PG1 over N1. There should be a term that looks up for P1. There should be a term that looks at something like 1 plus P2G2 over N2, you know, or log of 1 plus P2, I think I called it G2 over N2. So sort of these different terms should come into account depending on what case you're in. I think there's some intuition about that, but what I found in some of the exams that I looked at is a confusion about where to put the probability, because it seems like the probability is associated with the gain to noise ratio. And so a common thing I saw was trying to describe the expected rate on that second channel for a certain P2 that you put in, as with 50% probability, it would give you, you know, this SNR, and with 50% probability, it would give you this SNR. Okay, and to kind of describe this as the sort of expected rate for channel 2. But is this expression correct? It looks plausible. I mean, certainly gain to noise ratio is the thing that's random when we're putting half-half to each. But it's not correct. Why is it not correct? It's not correct for a very basic reason, which is that, think about how it actually would unroll in practice, okay? So sometimes the channel would have this gain, sometimes the channel would have this gain. When it has this gain, you would get this rate. When it has this gain, you would get this rate. So imagine just time averaging the rates over time. What you'll be doing is half the time you'll see this rate, half the time you'll see this rate, and you'll be averaging those. So where does that half go? Inside the log or outside the log? Outside the log, right? So that's a way to think about why it should go outside. But more generally, this has to do with the expectation of any function of a random variable. If you have that the metric you care about is not the random variable, but some function of it, that the expectation of the function is not in general equal to that function of the expectation, which is what this is saying. This is like the expected SNR, right? And this is the log, which is the log of the expected SNR is what we're saying. So the expected value of log of 1 plus SNR, when SNR is random, is not equal to the log of 1 plus expected SNR. Okay. And in fact, this is one of those things that used to trip me up when I first took a course in probability. And one reason it trips us up is that we don't even worry about this issue when they're deterministic quantities, right? If it's SNR, it's SNR. You want to kind of think about the average SNR, and you want to work with that. So it's very intuitive to kind of want to deal with log of 1 plus the average SNR. But this is generally not true unless that function is a linear function. If it's a linear function, you can write it this way. Expectations of linear functions are just linear functions of expectations. But when we have a nonlinear function like log, square, cube, anything like that, we can take the expectation of that quantity and move the expectation to just the random variable. Okay, so this is a very general principle. So it's something to be cautious about and be aware of. And so I think one place you could have gotten misled was just in formulating the problem this way. I think that's something to watch out for. So really the expected sum rate in this problem is this. Okay. And if at this point you got that formulation correct and you started down the path of working through the KKT conditions and so on, you probably had a very high chance of ending up with the right answer. In fact, if you did all of that correct, you'd get the right answer. A slightly different approach, which you can also do, and I would give most of the points, if not all for, is if you decided that because it's a special case of the general problem, you only have 2 channels. It's clear that whatever you want to pour, first of all, that there's no benefit to saving up power. You might as well use all of it, like whatever the total power is. That whatever you put into the first channel, you put the rest of it into the second channel. So if you want to just take that structure of the problem into account and reformulate, so it can also formulate as, so instead of doing the whole KKT stuff, can also formulate as log of 1 plus P, what was it, G1 over N1, plus, so whatever this P1 is, let's call it X, okay, plus, with probability half, it's the log of 1 plus P minus X, so where P is the total power, I think we just call it P total, minus X times G2 over N1, sorry, N2, plus half times the probability, I'll keep the half outside for now, log of 1 plus P total minus X, G2 over N2. So if you kind of think of it in this terms, it's a simple optimization problem with just one unknown. You just want to figure out what this X is. And of course, the only limitations in X is that it has to be bigger than 0, has to be less than P total. Okay, so there is this constraint that's implicit in it. But if you kind of wanted to write it in this form, work out the answer, and even ignore this for now, I would probably take it because you can always add this constraint afterwards when you kind of work through the implications of just solving this problem. So I would take that answer and give it a lot of credit as well. So if you just want to work with this, this is just some function of X. The whole thing is just some function of X, subject to this constraint. And so to solve for this, you could just take the derivative of f of X with respect to X and set it equal to 0. If you work this out, you will find, in fact, it's just a quadratic expression in X. And you can write an explicit closed form expression for what is that X which satisfies this optimization. And so long as that X lies within these 2 values, that is your answer that you're looking for. So one of 3 things will be the right answer, either the outcome of this solution or P total or 0. Right? So if the outcome of this expression tells you to choose an X higher than P total, then you pick P total. If the outcome of this expression tells you to pick a value smaller than 0, then you pick 0. But if it's in between, that's the answer. So you can kind of solve it that way. Yeah, so I won't work out the details here. Certainly they are tedious, no doubt. But I generally give a lot of points for just getting the approach right and sorting out some of the pitfalls. This is definitely something that I was assuming people would take into account, but I did see at least a couple of the papers were failing to work out this inequality. So one interesting extension of this that also the problem asks you to do is to consider the more general case, right? So sort of arbitrary PMF for each channel. So the methodology is still the same. You're basically in code, you would write down the rate on channel 1, right? So rate on channel 1 would have to be the expected value of the log of 1 plus SNR on channel 1, and then rate 2 would have to be the expectation of the log of 1 plus SNR2. And just like in this equation, both of those terms, the expected value in the first channel, the expected value in the second channel, would depend on x. They would both be functions of x. Right? So if you chose how much power you put into the first channel, you can compute the expected rate for the first channel. If you chose how much you put into the second channel, you could compute this. And you could simply try out different values of x. And for every value of x, compute this expectation, and see for which value of x you got the highest sum. Right? That's going to solve the problem for any arbitrary PMF. Especially if it's just 2 channels, you just try out different values of x. If it's more than 2 channels, it's a little bit less straightforward, because now you have multiple dimensions to solve for. You have to solve for x, for how much power to put in the first channel and the second channel and so on. So that might be a little bit trickier, and then that would require more thinking. But for the 2-channel case, it's just 2 equations that you would need to calculate. So this first one is going to be simply, the way you write this expectation for a discrete PMF is simply as, right, so in general, expectation of f of x equals, px of xk times the function of xk, and for all the xk in the support of that distribution. This is just the PMF value. This, in this case, is just log of 1 plus the power that you put into that channel times the gain to noise ratio, which is what we're calling the xk. Right? So these would be like the xk's. They would take on different values, and that's what the PMF would tell you. And so for every one of them, you would have a term, and you would just sum them all up, and you multiply them by the probability that each of them shows up. So, right? And really, this was just a special case of that. It's half times log of this value and half times the log when the gain to noise ratio is this value. That's just a special case of expansion of this type. So for any value of the power level that you're going to put into the first channel, you could compute this quantity because that would be known to you. This would be the value. And you have all of these multiple additive terms. You can work out this expectation, do the same thing for this, and then you would work that out. So at least, numerically being able to solve, even if you don't feel comfortable, working through some of the algebra, sometimes it gets tedious, sometimes it doesn't even have a closed form expression. But being able to think systematically about what is it that I'm trying to optimize. This is the objective function. It's the expectation of my performance metric, which means that I need to calculate my performance metric and compute an expression for its objective under different cases, take their expectation by multiplying by the appropriate probabilities, and then optimizing over that variable. At the core of it, that's the only thing we're really doing in every optimization problem. Right? So to give you an example and tie it back to our earlier discussion, so for the lemonade stand problem, the objective function will be a combination of the revenue, the stocking, overstocking that you might end up wasting, customer satisfaction, all of those components. There will be an expression that will be an f of x, where x will be the number of arriving customers. And you will say, what will be my revenue if the number of customers showed up was 1, if I stock only this much for this many people? What would be my revenue if 2 people showed up and I stocked that same amount, right? And I try that for different values of the possible arriving customers. And for each one of them, I figured out the performance. I then weigh them by the probability of having 1 customer, 2 customer, 3 customer, 4 customer. that will tell me what will be my performance if I stock this amount. That will be my expected performance. Then I measure my expected performance when I stock a different amount, and then a different amount, and then a different amount. That will generate the whole curve. So ultimately what I'm trying to do, if I want to, kind of see this as a big picture, is I have some expected value of f of x that depends on my design variable. Let's give that a name. Okay, so let me take a second to set up the problem we're describing. So we say the random variable or parameter, okay, with uncertainty is some variable x, and the design variable, okay, which we can control to improve performance, okay, is some, let's call that y. And this is deterministic, okay, not random right now. But this x, that's a random variable, right? Then identify the performance metric, which I'm calling f of x comma y. So it depends on both uncertain environment and the design variable. So in the lemonade stand example, the x is the number of people that show up, the y is how much I stock. In the airline example, x is the number of customers that show up, y is the number of tickets they sell. Okay, maybe even the price they sell it at. In the water filling problem we just looked at, x is the channel conditions for each of the channels, y is the amount of power that we're putting into each of the channels. Right? So in fact, I'm simplifying this by saying one variable. There may be a vector of variables. There may be many things that you control. There may be many things that are uncertain. Right? So more generally, we can do this, and it's sort of a random vector. And then y might be, a set of design variables. Okay. And then we have this thing called a performance metric, which depends on both. So your example here, this term of, so the overall performance metric is in the water filling problem, this f of x comma y type of term, the metric, is the sum of expected rates. So it's the E of log of 1 plus SNR1 plus the expectation of log of 1 plus SNR2. And the reason it depends on both the background uncertainty as well as your design variable in our problem here is that this SNR term incorporates both the random variable and the design variable. Because SNR1 is P1 G1 over N1, and SNR2 is like P2 G2 over N2. So assume this is like the random variable rather than the particular value. Okay. So if these are the random variable components, they're sort of are what are filling out the unknown part, and this is like your design variables. For any particular value of the design variable, for any of the design variable, and for any particular value of that random set of vectors, set of values in that vector, you can figure out what the performance looks like. And because you have this random quantity, you can calculate the expectation, and by taking the expectation, so if I take the expectation of f of xy, this is an expectation with respect to the distribution, right? Possibly a joint distribution if it's many of x. Okay, and is therefore, once you take the expectation, there's no more uncertainty. You've already averaged out all of the uncertainty. You've already computed for every possible value of y what this looks like. So this whole thing, you can think of it as some g of y. It is a deterministic function of y alone. Has no dependence on x anymore. Okay, and this is a very important point that you come to when you think about probabilities, that once you take out the expectation, there's nothing uncertain in it. Okay, so now the expectation of this quantity is just a function of y, of the thing that you control. So if you want to maximize this function, you just want to know for what y is it the highest, and that's the answer we're looking for. Okay, so maximize. This is the optimization that we're trying to do. So this is the goal. So to go back to the lemonade stand, the actual amount of revenue you will get, stock you'll waste, dissatisfaction you'll create, that will depend on how many customers showed up and how much you stocked. But when we take the average of that over all possible customer arrivals, all you're left with is the expected benefit, if you will, let's call that whole thing some utility or benefit, as a function of how much you stocked. And now you can just solve a problem which is how much should I stock? It's just a function of, that value affects what the expected benefit is. And then I want to know at what point does it maximize. And to go back to water filling, it's the same thing. So once I've taken the expected values of these things, the PMFs play no role. They've already been taken care of. Now I'm just left with a function that depends on the power levels, and I want to solve for that. Okay. So this general methodology where you have some function of x and y, where this is uncertain, this is under your control, you take the expectation of f of xy, which becomes just a function of y, and you solve it, that's the core of stochastic optimization. Okay, so it's a very general system that you're trying to solve. So this e of x comma y as a function of y, it might, be some function, and you're just trying to maximize it and find out what's the point at which this is maximum. And in this simple example, I'm saying it's one variable, but it could be a multidimensional problem as well. So ultimately, all of that stuff you learned in 503 gets used in real engineering through this, not always, but the majority of the time through a filter of maximizing the expected performance of your engineered system, despite the fact that there's uncertainty. Okay. So again, what's the thing to take away is that when you're building an engineering system and the performance depends on something that's outside your control, that's going to be uncertain, your best bet is to measure that uncertainty's distribution so that you can calculate expected performance for your choices. And then pick your choice which maximizes the expected performance. And this applies in almost, a wide range of settings. So for example, if you're trying to design a system that's going to be used by a lot of people, and they have individual variations in how they use your particular system, it may be that depending on the configuration of your system and depending on what that particular user's behavior is, there's a certain overall match that quantifies how good your built system is. But for whatever reason, you can only choose one setting. You can't change it per user. Then what setting should you pick? You should pick the setting that might maximize the expected benefit for over all of these users, or the expected match over all the users. So you want to characterize for every value of your setting what would be the expected benefit. Try all of your different settings and pick the one which maximizes the expected benefit. So that way of thinking about engineering in an uncertain system, that I want you to take away. So even if you forget the particular models, you forget how to do closed form calculations of expectations and so on, you can always compute expectations by just sampling, running simulations. You can calculate averages, right? And the law of large numbers tells us that calculating averages long term is the same as computing the expectation. So even if you can't compute expectations in closed form, this intuitive approach to doing a design for a stochastic system should make sense. Okay. While we're on that topic, let me mention one other type of objective that shows up is, so given uncertain environment X, design Y, performance metric f of x y. So approach one that we just talked about, you might try to do is you might try to maximize the expected performance, right? A different thing that you might try to do is say, well, I don't want to maximize my performance. I just want to make sure the performance doesn't go too bad. So this is more of a conservative design. For certain systems, what you want is not so much like improve your average case, but just hedge your bets against the worst case, or like some really bad thing happening too much. Okay. So a different way in which you might formulate that is you might want to, let's say, ensure that the probability that it falls well, what might we try to do? Yeah, we could try to do that. So, falls below some threshold is as low as possible. Okay, so this is a different goal. So let's think of this for a second. So maybe what I'm trying to say is, instead of maximizing my sum rate, I want to make sure that the probability that the rate I get is less than some number that I need is as low as possible, because maybe I have a rate outage type of a thing. I have an application that needs a certain minimum rate. Okay. I don't necessarily want to maximize the total rate over both of them, but I want to make sure that for both of them the rate satisfies some condition. Okay. So I want it to be kind of as likely as possible that this condition holds. Or sorry, it does not, low I said. So let's say there's a bad condition. I don't want that to happen too much. These two objectives are fundamentally different. And the second objective kind of makes it more clear that this is a random variable. So for any given x and their uncertainty and their distributions, your choice of y, for whatever value of y you pick, will still at any given moment in time only give you a random performance, right? And in the first case, the goal is I look at all the random performance I might get. So I might get like, just sort of imagine performance for a fixed y. So I keep my y at this particular number, and I just focus on what this f of xy looks like. It might just have a bunch of different values that it takes on. Okay. So, sometimes it's high performance, sometimes it's low performance. It's some distribution. Think of it as like a bunch of points that each time I do an experiment I generate. So in the first one, I'm just focusing on the mean value, which is like I take all of these points, I take their average. What is that average value I get? That's the average performance. And for some applications, that's what I care about, is on average, what's my performance. But if this is, for example, rate, and falling below some rate has some penalty associated with it, I can't even run my application, then maybe what I want to do is not pick the point which has the highest mean, but pick the point that minimizes the possibility that I fall below this level. And these two need not be the same. So maybe there's another point over here that has a much lower variance, right, where all the points are just scattered very close, very rarely goes below this threshold. Okay? So solving the second problem will make me pick instead of y1, it might make me pick y2. So maybe the expected, f of x comma y1 is higher than the expected value at y2, but the probability that f of xy falls below this threshold theta is higher for y2. Right? So in each case, all we're doing is we're taking this random variable and we're computing some deterministic quantity from it. In this case, the quantity is the average. In this case, it's the CDF evaluated at theta. Right? And so you say make your choice based on that. So this thing is also some function of y. So depending on what y you choose, you might choose this probability. And so you might want to choose that probability to be different. So it's not always the case that for these stochastic problems we want to maximize the expectation. Sometimes we want to minimize an outage probability or something else. Right? Even when we talked about link qualities, we talked about these two metrics, the average bit error rate and an outage probability. They're kind of getting at these two types of objectives. Okay. So when we do stochastic optimization, sometimes, for QoS reasons, for example, latency, that's another good example. So do you want to build a system which has the lowest average latency, or that guarantees with high probability that the latency never drops below or above some number? Right? The second one, for quality of service reasons, is often more useful. So in a lot of control applications, the latency going above some number means it's completely, you can't stabilize your system. So minimizing that probability is important. You might still not be able to guarantee it 100%. So maybe even at this point there's some probability it'll drop below the threshold, but at least you want to make sure that's as unlikely as possible. So that's what a lot of probabilistic optimization is about. So I think these ideas are very general. They can be applied even without using any calculus in a real engineering design. They are just saying that when you have uncertainty in your system, compute the metric you care about and choose your design parameters to maximize that metric of interest. Okay. All right, so I want to kind of wrap up on the link layer, but there are two more topics that I thought we should touch at least briefly on. One is we mentioned but didn't really get into this Rtscts mechanism for CSMA protocol, so I'll just mention that briefly here. So in your even for your assignments, you saw that there's sort of different numbers if you use Rtscts for 8211 versus you don't. And what is this mechanism and why would you use it or why would you not use it? It kind of goes back to an early identification of a problem with CSMA by researchers called the hidden node problem or hidden terminal problem. And sort of graphically, here's a simple example to see it. You have transmitter 1, transmitter 2, and a receiver. And both transmitters, let's say, are trying to talk to this receiver. And the way CSMA works is that each transmitter is supposed to make sure that the channel is clear before it will transmit. So it will sense the channel, and if it's free, only then will it try to transmit, right? And in the picture here, on purpose, we've drawn these two transmitters to be far away from each other. So even though they may be in range of the receiver, they may not be in range of each other. So when this transmitter tries to send, it may not be aware that transmitter 2 is transmitting, or vice versa, and they can actually both transmit at the same time and cause a collision at this intermediate receiver. In fact, the same picture would hold if they were not even trying to talk to the same receiver. Maybe transmitter 1 wanted to talk to this receiver, transmitter 2 wanted to talk to its own receiver over there, and when it sensed the channel, everything was fine, so it went ahead and transmitted. Receiver 2 is happy, but receiver 1 still sees a collision because it's a broadcast medium, they will collide. So the key problem here is that sensing. So the main issue is, the collisions, sort of unexpected collisions, if you will. Okay, you would say unexpected in that the whole idea of CSMA was to try and reduce the number of collisions, and now we're seeing collisions where They don't even sense that the channel is busy, and they're sending, and there's a collision, right? And even though the channel might actually have been occupied in the sense that this transmitter was already talking, this receiver was getting a lot of interference from this transmitter, but when this transmitter checked the channel, everything was fine, so it went ahead and sent and caused a collision. So it's unexpected in that sense, right? So the problem occurs because sensing is at the sender, and the collision is happening at the receiver. So ideally, what would happen is that the sender would ask the receiver, are you available? Are you sensing the channel to be free at your end? And I also check the channel at my end. We both see that the channel is free, then we should communicate, right? And so to solve the problem, Rtscts is introduced, and basically it's a handshake mechanism. It's a way for the sender to ask the receiver a request to send, and for the receiver to say, yes, I'm free, you're cleared to send. Okay, it's as simple as that. So RTS is a request to send that the sender sends, and then the receiver will send a clear to send, okay, if channel is free at receiver. Okay. So the other benefit often in implementation is that when the clear to send message is sent, it is broadcast as well to all of the other transmitters nearby, and they become aware. So when, for example, in this case, let's say transmitter 2 had started to transmit first, when it sent its request to send, the receiver will send a clear to send, which will even be heard by this transmitter. And so this transmitter will not even have to send a request to send. It may be aware that there was a clear to send message that came from this node to transmitter 2, and it typically specifies a certain duration called the nav duration. And for that period of time, it knows there's not even a point asking. So it'll even defer requesting in that case and can wait till that period is over and then make a request to send. And so sending out this clear to send also sends a signal to other transmitters that I'm in the middle of receiving something, don't send right now. So it also deters communication, it reduces collisions, and from that perspective, it's good. The trade-off is that, so it does reduces collisions, but has higher overhead. And the overhead is simply having to add 2 more packets of exchange before data can be sent. And so typically, as you can imagine, if you don't want high overhead, you only use it if the data itself is large. So typically, we only use Rtscts when your packets are very, very large. And in fact, in most commercial implementations of 82.11, Rtscts is typically turned off by default. It doesn't end up being very useful in typical usage unless the packets are really large. But it is a particular way to solve this problem called the hidden node or terminal problem. The other thing I want to mention briefly in the context of medium access, and maybe I'll expand a little bit on it in the next class since we'll potentially run out of time here, is a new class of MAC protocols have been developed in the last 10 years, I would say the last 10, 15 years, for low power wireless embedded devices. And these types of devices are a significant part of the future IoT systems. Okay. So you might have heard a lot of buzz about IoT or Internet of Things. The best example of it commercially that's already been very successful for a long time is like the Nest thermostat. Right? It's a device that's in your home that's monitoring temperature, it's monitoring and controlling the actuation of AC and HVAC systems. Increasingly, we're talking about deploying many, many objects in our house and having them be able to communicate wirelessly with other devices. And unlike a lot of traditional wireless nodes, whether it's your cell phone or your laptop, where periodically you can plug them in for power, as you increasingly try to embed your wireless devices and radios in things that are not plugged into the wall, they're running on batteries, you have to be very careful about how much data they communicate, how much energy they use up. And so you have to end up putting them to sleep a lot. Okay? And so big component for IoT platforms is that they are often involve energy constrained devices, maybe running on batteries, okay, that for long lifetimes must spend a lot of time asleep. So here's a problem of medium access then, is you have two devices, and they spend a lot of time sleeping. And they want to send data to each other. So the obvious thing would be they should learn when the other one wakes up. They both should know when they wake up, and they should communicate to each other. Right? So option 1, so here's device 1, device 2. Option 1 would be schedule the sleep periods and only communicate during the known active times. The problem is we can't always do this for two reasons. So problem 1 is that these low power devices, okay, are first of all typically using cheap hardware and will basically get desynchronized very quickly. What I mean by that is that you might tell them, okay, he's going to wake up in a few seconds from now, and it's going to keep doing that. So you tell these nodes, wake up every 3 seconds, and then you can communicate. But if your clock is running faster or slower than the clock of the other device, you might both initially wake up every 3 seconds, but over time the clocks start to drift apart. One of them is moving a little bit faster than the other. It wakes up a little bit sooner and sooner and sooner and sooner. Pretty soon they go out of sync from each other. So this one wakes up, the other one's asleep. The other one wakes up, this one's asleep. So they will lose the synchronization that you built in and will no longer be able to communicate. So that's one thing that happens with these low power devices. Typically you want these devices to be tens of dollars, not more than that. So that's one problem. The second problem is mobility. So it may be that this device is doing some sleep cycling on a deterministic cycle, but this device just showed up there. Nobody ever told it when the other device is going to wake up. Okay, it may not be a few seconds, it might be a few hours. Okay, and if you simply don't even know what the schedule of the other device is, what can you do? And so in both of these types of settings, kind of scheduling the sleep periods and only communicating then, this option that's known as synchronous sleep may not always be feasible. It is sometimes feasible, but not always. So the second option is called asynchronous sleep. So the idea is that they can sleep whenever they want. They don't need to have pre-published or agreed upon when they're going to wake up. But you still want them to be able to communicate and catch each other at the right time so that they can send data to each other. So there are broadly two ways of doing this. One is called transmitter initiated. And the second are called receiver initiated. So the transmitter-initiated scheme sometimes goes by the name of low-power listening as well. And the basic idea is that the receiver will stay asleep and periodically wake up to check on the channel. So it sort of sleeps, wakes up to check, sleeps, wakes up to check, and so on. The transmitter, if it has nothing to transmit, stays asleep. The moment it has data to send to the receiver, it starts, it can't start transmitting data, of course, because the receiver is not awake. But what it does is it typically starts sending what's called a preamble. Okay. And the idea is that the receiver sees, when it wakes up, that the channel is busy, sees this preamble, and that causes the receiver to wake up at that point and stay awake. And the transmitter sends a long preamble, and after the preamble, it sends the data. And because the receiver will hopefully catch the preamble and stay awake, when the transmitter sends the data, the receiver is awake. So which means that the common case is just looks like this. The receiver, if there's no data, right, so no data, then it just sleeps most of the time, wakes up a little bit, sleeps most of the time, wakes up a little bit. The fraction of time you're awake in each epoch is what's called the duty cycle. Is the wake up over total period. And you can tune that depending on your application's needs. You can make it a 10% duty cycle, a 1% duty cycle, and so on. Right? So that's sort of the common case. If there's no data, you get to have that duty cycle sleep. And that duty cycle can be low. It can be like 1%, which means that whatever your battery power is to last, you're only using, you're basically extending the usage of that battery by 100-fold factor if there's no communication. So your system can last long. When there is data, though, it's able to wake up and get the data. So it's, even though it's getting a lot of the sleep benefit, the energy benefit of sleeping, when there is data, it's able to wake up and pick up the data. Of course, a lot depends on how long the preamble is. Right? And the preamble clearly has to be long enough. So if the preamble was short, what might happen is that the transmitter wakes up, has some data, does a little bit of preamble, starts sending data. This one wakes up in the middle of the data transmission, has missed data. Or even worse, the preamble was so short that the data itself got transmitted before the receiver woke up again. So clearly the preamble has to be long. In the worst case, what might happen is that the transmitter wakes up just an instant after the receiver shut down the last time. So in fact, your preamble has to be long enough to catch its next wake up. Right? So preamble has to be the total period length. Okay, so if you call this a total period, let's call this some T and this capital T. Your duty cycle is like T over T. The preamble length will have to be bigger than that total length. Now, over time, people have developed slightly more efficient versions of this where the preamble doesn't have to be one long wake-up time, but sort of a series of short packets. You just want to make sure that when it wakes up long enough to receive one of those packets while that preamble period is going on, just to reduce even the preamble energy consumption. So there's some implementations that have improved that, but the general idea is this. So this is called transmitter-initiated asynchronous sleep or asynchronous duty cycle. Okay. And the benefit of this approach is that the receiver most of the time will guarantee a very low energy usage. And it's transmitter-initiated because it's only when the transmitter has the data does the whole wake up happen at the transmitter and the receiver's woken up and data is communicated to it. So that's the sense in which it's transmitter-initiated. The opposite scheme that's called receiver-initiated would do the opposite in that the transmitter basically has its own wake-up cycle now. And then the receiver so in this case, the receiver was just waking up, right? So the transmitter was transmitting. In this case, the transmitter just wakes up and doesn't transmit, but it does wake up periodically.
It's your 5-minute warning.
And the receiver will periodically wake up and send a probe message. Okay. So let's say it does that. So this is send out a probe message. And what this probe message will do is it asks, is there somebody who has data for me? It's more of like a pull. Whereas the earlier scheme, the transmitter-initiated scheme, is more of a push, like I have data, so therefore I'm trying to wake up the receiver. Here the receiver is the one that has to do the job of saying, does someone have data for me? In fact, the transmitter does not even have to do any duty cycling. In the simplest version of this transmitter might even just stay asleep if it has nothing to send. But if it has something to send, what it would do is it would wake up if it has data. And when it receives this probe, because it's awake, it has data to send, so it just wakes up. It's not sending anything, it just wakes up. It hears a probe from the receiver saying, do you have something for me? And you say, oh yeah, I do have something for you. You kind of act that back. And when it hears the act back, the receiver wakes up. And you can start sending your data to the receiver. Okay. So the difference from the transmitter-initiated scheme again, on the transmitter-initiated scheme, the receiver stays asleep, wakes up periodically to check the channel, but the checking is a passive action. It doesn't have to send any data. The transmitter stays asleep. When it has data to send, it starts sending a preamble. When the receiver sees when it's during its wake-up time a little bit of the preamble, it stays awake so that data can go from the transmitter to the receiver. So it's sort of all getting pushed from the transmitter. In the receiver-initiated scheme, the transmitter, in fact, when I first drew this, it wasn't even necessary. The transmitter might just stay asleep all the time. The receiver just keeps asking, hello, is anybody out there? Do you have anything to tell me? And if there is a transmitter that has data, it just wakes up and holds on to the data, waits for a probe from the receiver that it wants to send data to. When it hears the probe, it acts it. The receiver says, okay, now I'll stay awake to listen to the data, and that's when you send the data. So the data communication only happens when the probe is received and after an ACK is sent so that the receiver is awake. Right. And of course, this ACK has to get there before the receiver goes back to sleep after its probe. So it sends a probe and it waits for an ACK. Okay. So it sends out a probe message and waits for an ACK, sleeps if timeout occurs. So these asynchronous duty cycled sleep-based MAC protocols. There are a number of particular examples of this in the literature. Their schemes go by names like LPL, XMAC, AMAC, etc. A lot of it has been developed for low power wireless /IT devices. So this is a completely new development in medium access that's really only happened in the last 10, 15 years. So I wanted to make sure everyone here is aware of those types of developments that are happening in the Mac space. So starting the next class, we're going to move to the network layer, and we'll talk about different routing metrics and routing protocols for multi-hop wireless networks. Okay.
This concludes EE 597 with Professor Krishnamachari on Wednesday, July 13, 2016.